Okay, so we are after these structure constants. We are after learning more about the CFT data of n equals 4 superangles. In particular, we are after this structure constant in one operator which is non-trivial and two BPS operators. In particular, we might want to consider a 4-point function where two operators are something like this and two other operators are something similar. And in the middle, we will have this operator O spin being exchanged, and therefore we definitely need to know this structure constant. Yeah? Is it clear? Now, just one comment about what we were discussing with Kosti related to why did we choose this setup where we put some n here rather than putting n equals 0. So what is the difference? When n is equal to 0, this is what we call an extremal correlator. It's a correlator where the length of one operator is the sum of the length of the other two. It's the case where there are no weak contractions between two of the operators. And when you have such cases, things get a little bit more complicated from a large n point of view. So let me show you what happens in that case. So the question I want to ask is, I have my operator, and there is a mixing that we have to solve by diagonalizing this Hamiltonian. But we have to be careful, or maybe we should be careful, that there is also mixing that we never discussed in this lecture with double traces. This operator has a little bit of double trace in it, but this mixing we never care because it comes with some powers of 1 over n. Should we care about this mixing with double trace? No, here definitely not, because you see, compare this diagram with this one where I just replaced the bottom by a double trace. We lost one loop of color here in the middle that gives a factor of n. So the graph on the left is much bigger than the one on the right. And this one furthermore comes with suppression. So definitely we do not need to worry about this guy. Okay? So it is fine to just take these pinches and start connecting them. However, consider a case like this, where I have
coefficient is also suppressed by 1 over n.
That's what I said, yeah. Coefficient also comes with 1 over n, so it's two effects in the same direction, we don't care at all. What about in this case? Suppose I have an operator here with some z's and the crosses indicate x's or x bars. I don't care now about the derivatives for this exercise. There is also a possibility, instead of these x's contracting with x bars, they could come down, and then you would need in the bottom to have an operator that has z's and x's. It's a bigger operator, but you could consider this 3-point function. Now, this 3-point function is much smaller than this one here, because by breaking this line, you create an extra boundary, so you gain the factor of n. So actually, in this case here, which is an extremal case, it is relevant to consider the mixing with double traces.
But they are of the same order because of 1 over n.
Yeah, so then they would be of the same order and they would be important. So in this case, it is not true that I can ignore the mixing with double trace. I have to keep them, they are relevant. They are not irrelevant like here. So by considering this small bridge upstairs with n, I make sure that this object is okay and I don't need to worry about mixing with double traces. So to be very explicit, suppose I consider this 4-point function, these two operators and these two here. And in the middle, I see what is flowing. And the operators, I can label them by twist. Twist 4, twist 6, twist 8, and so on. Twist is dimension minus spin. For twist 4, for length 4, they must be single trace. Otherwise it will be suppressed in n. But starting at twist 6 and so on, when the 6 fields go here, you start getting double traces that you also need to sum over. At least naively, you need to sum them over. I think there should be a way of getting rid of these double traces and bootstrapping just using single traces in a clever way, maybe using a smell in amplitude or something like this. But in the way it is normally formulated, at higher twist, you need to consider you need to consider double traces. But for the leading twist, like twist 4, so if we analyze the leading twist, the leading twist, here only single traces will flow for the reason that I explained here. Okay? Does it answer your question?
Can I understand? So in this picture, will there be equivalent effects like you said, or not? Because the effects goes in the middle and they can be integrated.
So if here you have an operator of twist 6 or higher, so here it will be, you mean an x and an x bar. Yeah, that doesn't matter. But It would be an operator of total length 6. So if the length in the middle is 4, you are guaranteed that you must be in one of these cases here.
But also, I mean, you will have to incorporate x expression in the middle, but then you can't have them at the right.
You can have them what?
Then they can't manipulate with y in the right.
No, but x and x bar is neutral. X and x bar is neutral. So there are operators here in the middle. You could have an operator which is this trace of z, just the product of these two fields times this trace, z x bar, plus the same thing with x replaced by y. So this could be a double trace operator. So suppose you have this double trace operator here in the middle. It will definitely contribute at the same order, like Costi was saying. Because the 3-point function is enhanced, and this operator will definitely be there. And also, if you have a single trace plus 1 over n times this, it will also contribute. If you have a single trace of z, plus something like this, it will definitely contribute. But you will distinguish these states because they will have length 6. So they will have twist 6. So if you go for the leading twist, which in this case is 4, you know that if the length is 4, it means that the x and x bar were annihilated and you produce just a single trace by counting 7. Yeah. Is it clear? Very good. So now, we would like to make a connection between this structure constant here and the scalar products defined there and written down here. Between these scalar products. And the claim is very simple, is that this structure constant is actually up to some simple combinatorial factors which are given by the following. There is some binomial of what? L plus n choose n. And up to some simple factors here. Up to some simple factors, it is exactly this AL over B. Okay? So this is, if you want, the main claim of today. Is that these two scalar products are exactly what we need to compute this object. So let me just give you an idea. And the reason why I'm not very interested in giving a straight, rigorous derivation is because, as you see, all the ingredients are given. The beta states are given. You just need to do weak contractions. You have this statement. You can check it in many examples. You can check it in Mathematica. It's a true statement, and you can convince yourself. Everything is well defined. It's just a question of put the wave function here, do the sum, and do the weak contractions, compute, and you will find this result. Okay? Given that it is totally well defined and conceptually clear, I don't want to spend too much time on it. But let me just give you a flavor of why this is indeed what we expect. And the reason is the following. It's very simple, actually. You see, here you have some derivatives, like 4 derivatives acting here, and 3 derivatives acting on the left, and 4 derivatives acting on the right. Now, when a derivative acts on these propagators here, they generate, this is a T plus, it acts on the propagator, it generates a dependence x12 minus over x12 square to the power of how many derivatives there are on the left. Let's call them m. Okay? So let's say m derivatives here. And these propagators that act here, they generate a space dependence x13 minus divided by x13 minus square to the power of the number of them, which must be s minus m. Okay? It's just a derivative of 1 over d plus of 1 over x squared is x minus over x squared. Is it clear? Now, on the other hand, you have to sum over all the cases, when all the derivatives are to the left, when all of them are to the right, when 3 of them are here and 4 of them are here, and so on. But you can group into the cases where m derivatives are here and s minus m are here. And they give a very distinct space dependence. And at the end, you know we must reproduce this space dependence here by conformal symmetry. Because you know that you must reproduce this case here, you can focus on the case where m is equal to s. You can just focus on, you expand this binomial and you look at the coefficient of x minus over x squared to the power s. Then you can check that the other ones give the same thing, but you can focus on the leading order one. So we focus on m equal to s. So fixing on m equal to s means that we want to study the contributions where all these derivatives are rather on this group. They are not here, they are all on this group. And then what do you compute? You compute the wave function, and you have this operator, and you overlap with the top. So the structure constant is proportional. You sum over 1 smaller or equal than n1, smaller or equal to L, the wave function psi of n1 ns, this is here. And then the contraction of this operator with a vacuum upstairs. But note something nicer, these factors that we have here, 1 over mj factorial, precisely disappear because when I have two derivatives, I get 2 factorial from taking two derivatives. And that cancels the 1 over 2 factorial. So those factors just give 1, and then I just contract. So it is literally just this. Just this wave function. But what is this? This is just take the wave function with equal weights if you have an homogeneous gas in the beginning of length L, of small length L. So this, by definition, is A. Okay? This is what we wanted to show. Similarly, the norm appears because you have to divide by two-point function to normalize the two-point function to 1 if you want the structure constant to have a physical mean. Okay? And then you put all the factors together carefully, all the combinatorical factors. This here, for example, is the two-point function of the 2 BPS operator, just the number of ways of choosing where to put the x's in the C of length L plus n and so on. Just combinatorical factors due to the BPS state. So this is our prediction for the structure constant. Okay? So let me just
in this formula, can you say how to get this mathematical factor?
This factor here?
Yeah.
No, this was what I... So let me repeat the logic. I put all the derivatives here on the left.
No, but before you even start with compute.
How did I know that this is this?
Yeah.
This is just conformal symmetry. The 3-point function must transform with appropriate weights. It's a tensor now, it's not a scalar. So the same argument that fixes these 3 factors, when you have spin, also fixes this factor here to be of this form. This is a known statement in conformal symmetry. When you have an operator of spin S and 2 scalars, it's this formula. When you have more operators with spin, there are several tensor structures, and there is more than one structure constant. So if you ask what is the 3-point function of 3 operators with spin, it's not true that they are given by one number. They are a sum of tensor structures.
What is the most powerful formula of this type? Is it called the same type as the
Yeah, I think the best reference for studying this, there is some very old paper by some Bulgarians that I forgot, but it is cited in a more recent and more modern language by Penedonas, Costa, Karnal, and Slava Hishkov on some spinning correlators. And they study exactly what is the form by conformal symmetry of operators with spin. But again, if one operator has spin, it is fixed by conformal symmetry. If more than one operator has spin, you have a set of structures, and there are several tensor structures, and we should compute one structure constant for each of these structures. More questions? So, slide. So let's go a little bit and just very quickly implement this structure constant. There's almost nothing to do. Here it is. It's done. It is just binomial coefficients, A over B. We already implemented before. And now we can ask, say, an example. Let's compute. Let's take, remember that these were the roots that gave the spectrum. Okay? There is 1 element, 2 elements, 3 elements corresponding to the 5 solution. Take one of them and compute the structure constant. And this is what we get. Okay? So this is a number, okay, doesn't look anything special, this is what it is. Any question here? we could compute another operator, the second solution, and it would be this and so on. Okay?
I just looks like files.
Sorry? Let's compute another. Okay. So now let's just play a little bit, because actually some of these results are well known. So this energy section, it's done already. It is just computing the energies for spin 2, remember? And I'm showing that it agrees with harmonic numbers. What about the structure constants? Structure constant is something nice. We can compute C1, 2, 3. Again, let me remind you. This is the length 2. This is small l is 1. Now we are considering twist 2. We are considering 2 fields here, 1 line. So we are considering the simplest possible case for twist 2, which is the case where we have just this. Okay? Z with derivatives here. Z bar x, x bar, z bar. Just the simplest possible case. You know this wave function explicitly. You can compute these objects, and actually this is known to be something nice. So let's see that we reproduce. So we can put 1, so 1 is n, 1 line, but actually it's independent of n, but okay, we can put it to be 1. And we can ask twist 2, spin 2, for example, the first one. There's only, as we know, for twist 2, there's only one primary, and indeed, if we have this element 1 just takes out the last brackets, just so that it's a list. But that's it. And this is the number we will get. Okay? Doesn't look particularly nice, but then we square it, and it looks a bit better. We could look at the same thing with spin 4, and again, it doesn't look particularly nice, and we square it, and if you see, 2, 8, 5, and now it starts repeating. So clearly these are rational numbers. Okay? So now we can just compute them, all of them, so up to a spin 10, and here it is 1/3, 1/35, 1/this, 1/this, 1/this. And this is nothing but this ratio of factorials, and this was a known result that 3-point function of twist 2 operators are given by just as factorials. You can compute it very easily. If I can do it if you want, by using the forms for this primary twist 2 operator. And as we see, we just recomputed this in kind of a complicated way. Okay? So now let's make contact with what we started in the morning, with the bootstrap and with 4-point functions. And let's reproduce these results that we got from this integrability spin chain approach from a 4-point function. Let's take a 4-point function and get these numbers out. So what we want to do, we just want to take a 4-point function and expand it in conformal blocks and read off the coefficients which are the structure constants. So what is the simplest example that we want to do to be able to extract this twist 2? Well, we do exactly as I did there in the corner, a simple example. We can consider a correlation function of trace of zx, trace of zx bar, trace of z bar y, trace of z bar y bar. Do you agree? This correlation function, to leading order, will have z squared flowing from here to here, with the derivatives as well. Is it clear? So now let's compute it. This we can do. So let's draw 4 points. Let this be point 1, 2, 3, and 4. And let's see, so the x must connect from here to here. So this is x, and here x bar. The y must connect from here to here. Y bar. these lines, z, z? Well, there are two diagrams. One where you connect z here and z here, plus another one where you connect like this. They are both planar. Of course, I can draw the line going outside. So what do they give? They give 1 over, so let's do this one first, x1 minus x2 squared, that's a propagator, x2 minus x3 squared, x3 minus x4 squared, x4 minus x1 squared. That's the propagator of the square going around. Okay? Plus a similar term, let's do it. 1 over, what do we have? We always have x1 minus x2 squared and x3 minus x4 squared. We agree this is the propagator of x to x and y to y. But now, instead of 2 to 4, we have 2 to 3. So actually this was the second one actually. So the first one, this one now is 2 to 3. Yeah, this is the second one, now we need this one. 2 to 4. And 1 to 3. Is it clear? Okay, with the numbering that I chose for this picture, it's like this. Yes? And now, I will just do what I told you we should do. We factor out some trivial dependence. What was it? If you see the notes, it's x1 minus x2 to the power 2 delta. Delta is 2, so to the power 4. x3 minus x4 to the power 2 delta, which is 4. And now when we factor this out, so the first term, we take out this factor, but here we only have power 2, so we take power 4, so we get 2 of these guys upstairs. And that is the definition of ZZ bar. Is it? Sorry, 1, 2, 2, 3. No, that's not. Let's look at the second one. Take out x12 to the 4 and x34 to the 4. Then you get them upstairs. It's ZZ bar. So the second term gives just ZZ bar with this definition here. And the first term gives ZZ bar over 1 minus Z, 1 minus Z bar. It's the ratio of the two cross ratios. Is it clear? Yeah. And what is this? This is the amplitude of Z and Z bar that we said we should expand in C 1, 2, delta L, C, delta L, 3, 4 times the conformal block, which is given here. Okay? So now our exercise is very clear. We should take this rational expansion, the rational expression of Z and Z bar. It's very nice. And we should write it as a linear combination of productive hypergeometrics. Okay. It doesn't look like the nicest thing, but okay, let's do it. Okay. So now time to go to Mathematica and do this simple exercise. Again, very explicit. All we have to do is start with this expression for A that I'm now almost covering. And we write it as a sum of this conformal block. Okay. So now I go to slide mode. I was on slide mode. I forgot to go to on. Could you see what I was writing? Yeah. With a lot of suffering. Well, sorry about that. I can put it back and turn on the light and then push back. It's better? Okay? So just the two diagrams, they give these two terms, and when we factor out what we said we would, we get this ZZ bar times this simple function, and now we should expand it in this way. Please remind me about these lights, I forget sometimes. Okay. So let's do it. So let's just see how it works here. So I remind you we have these C's here. We will later run this. These are the C's that we got. This, the square of the structure constant. So here is A3, the reduced 4-point function at 3 levels. This is what we computed. ZZ bar plus ZZ bar over 1 minus Z1 minus Z bar. Right? This is what we said we just computed now in the blackboard. Here we have the conformal blocks, And this is after taking out, remember I said the conformal blocks are almost a function of z plus a function of z bar. After you take out this factor, I'm going to take out this factor and multiply the amplitude by this factor. And the reason is that it's always a pain, you know, you have something like f of x minus f of y over x minus y, and you want to expand this in small x, small y. And actually this has a good limit, it doesn't matter which order you do, but if you are a bit not careful, you will soon get very nasty looking expressions that look very bad. It's a bit like, imagine I tell you to expand this at small x and small y. This of course has an order of limits, you should say first x or first y. It's not well defined to say small x, small y. But if you have f of x minus f of y, then it's okay. However, if you may first expand, so better to don't expand things in small z and small z bar if you have 1 over z minus z bar, multiply by dimension. Alright. So these are the conformal block we just asked. F strip, say, dimension 4, spin 2, function of z and z bar. And this is what it is. These hypergeometrics collapse into something nice. Dimension 10, spin 12, z and z bar. Okay, this one did not simplify. Let's see, function expand. Okay, yeah, some logs and so on. Okay. It's what it is. Some relatively complicated expressions of logs and so on, but okay, not too bad. And then what we do is very simple. Okay, we just put some cutoffs because we will expand in z and z bar, and we don't want to expand to infinity. And then we define this Gothic f, and this Gothic f for say spin dimension 10, spin 2. It is just the expansion of the conformal block at small z and z bar. We just take f strip and expand it. On the other hand, so we make this series. On the other hand, and here it is just generating this sum of structure constant square times those conformal blocks. Okay, and this progress indicator is just that it's funnier. And then we do the same thing. We take the 3-level amplitude, multiply by the z minus z bar over z bar because we took it out from the conformal blocks, and we expand in z and z bar as well. And then we subtract both. The expansion, again, let me just show what this expansion looks like. It looks like a mess, like a sum of many terms. It is just take the conformal blocks and expand them. You subtract the result. And what about this expansion? This looks nice. See? Just the expansion of that nice function gives something nice in it, not surprising. And then we subtract both, and we solve and find the coefficients of the conformal blocks. So if you run this data is a list of replacement that tells what the coefficients of the conformal blocks are. And we can make a table to see what they are. Here is what it is. So the column is the row is the dimension, and the column is the spin. And see how I can do it like this, and then take this. And what we see here is, okay, this column is just 0. You must have some dimension. Sorry? There is a laser point. Okay, so this here, I prefer this. So this 2 and spin 0. This is just a BPS case where the spin is 0, so it is just the exchange of trace of z squared. So this 2 here, for example, if we were to compute with higher loops, we will get a 0 here in this line if we were extracting from higher loops. Because this guy is BPS, it is just 2 and that's it. And here, this is dimension 4, spin 4. We are jumping in units of 2, because when you have scalars, these scalar operators, in the middle you only have even spin. And this is also why in the very beginning of the lecture today I only cared about even spin. And then we get 1/3 for that 3.5. Square, because it's one from the left, one from the right, they are the same. And then when you have spin 4 and dimension 2, 4, 6, you get 1/35, tac, 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 tac. And then these numbers, you can compare with what we got before, and you see that exactly sitting on this lower diagonal for twist 2, you get the numbers that you get here. Okay? So it's really this simple. You just extract from a correlation function, you just expand it in conformal blocks, and you generate this kind of table.
So C1 to 3 is actually square.
C1 to 3 squared, yes, sorry, yeah, C1 to 3 squared, which is the product of these two. What we are extracting, what we call C squared, there is the product of these two C's. They are the same, so it's just squared. And we see that we get this very nice table, zeros almost everywhere. This is just a coincidence because the twist is very small. Let's do another example of extracting data. How much time do I have? No, after 1 hour. Okay. So let's consider now another case, where the tree-level amplitude is this. So let me just tell you what case are we considering. It's a more interesting case, where now we don't want in the middle to have twist 2, but we want to have twist 4. So we want to consider now one of those more interesting cases where now you consider z, z, x, z, z, x bar, z bar, z bar, y, z bar, z bar, y bar. Okay? So it's the analog of what we did here, except that I'm adding an extra z and an extra z bar at the one side and the other. And now, at the leading twist, when I consider now this leading contraction, now I will have diagrams like this. The x and the y are always like this, but now I have different diagrams. I have two legs going like this, and two legs going like this, or more complicated cases. Now the combinatorics are a bit more complicated, and the result is what is written there. Okay? The result is just a simple rational factor z and z bar. It's just that you have more diagrams and you get that. Okay? Nothing surprising. Okay? So this gives, for twist 4, some amplitude, some reduced amplitude of z and z bar that we will again expand. And here in the middle, we should find twist 4 and higher. Whereas before started at twist 2, now we should see that it starts at twist 4. Because, okay, the x and the x bar can annihilate, but at least 4 units of z must propagate. So it should start at least with twist 4. So we should see that if we just run exactly the same code, remember that this table here at the end started immediately below the diagonal, indicating twist 2. Exactly the same code should start one line below, indicating that it starts at twist 4. Is it okay? So now let's just do that. Let's just run exactly the same code. So we just run exactly the same thing, and we generate, but I should run the tree-level amplitude, otherwise it's exactly the same thing. And we just solve, and this is the table we get. Okay? So much more interesting, much more complicated, but also much more interesting. We get now, again, nothing in the diagonal, of course, nothing now for twist 2, a bunch of zeros in the sub-diagonal, and here is what we are getting for twist 4. 4 instead of 2, that's the BPS result again, and then 7/5, 16/43, this, and this. And then we also get things here. In particular, I think this is contamination not only but also by the double traces and so on that we discussed in this example that I said before. It was exactly this example. But this line here, this upper diagonal here, this diagonal we should be able to match exactly against integrability. Right? Do you agree? So how do we match that line against integrability? So we can try, let me first close this section. I'm taking short notes. Let's try to compute C1, 2, 3, length 4. This is small l equals to 2. It's the case where we split, where we have two, we split this in two. Say n equal to 1, there's just one x and one y. And we compute this for spin 4 length 4 and spin 2, and we take one of the solutions, and we square it. And this is what we get. It doesn't look like a 7 over 5. Right? This, we took one solution. This is not 7 over 5. If I remind you that 7 over 5 is 1.4. But okay, remember that there were several solutions. For 2, how many solutions? Actually, there are only 2 solutions in this case, it seems. Yeah, there are 2 solutions. We could take the other one also. And it's also not 7 over 5. Sorry? Maybe we could try the sum. Okay? And this is 7 over 5. So this is something nice that we are seeing here. And this is exactly what we expect. So what do we expect to get? We expect at leading order the energy of all the states of L equal to 4 and any spin. They are all degenerate. It's only at loop level that we start lifting the degeneracy. So when we sum this, let's say that we have twist 4, which is what we are interested, plus higher twist. And now we are interested in this twist 4. So what is this twist 4? This twist 4, we can say it's a sum. We sum over all states delta and S, where delta minus, where L minus S equal to 4. This L is equal to delta plus the leading order. Okay? Of structure constant of delta and S square times conformal block. But there is a big degeneracy, so I can write this as a sum for a given spin S, and for a given spin S, I should sum over the solutions to Bethe ansatz equation of the structure constant that depend on those beta roots square. And it's this sum, because we cannot distinguish two leading order, that comes multiplied by the conformal block. Is it clear? Because two leading order in perturbation theory, all of them have the same dimension. They are degenerate. All of them have dimension L plus S. So there's no way to distinguish. So what we should be doing is solve Bethe equations. Take all the solutions that we computed. For each of them, compute structure constant, square, add them all together, and this is what should give these nice numbers. So this is what we should do. Let me do it from scratch, and then we open the section and see what is there. So what we should do is, we take a given solution of a given spin S, okay? And we take solution number J, and we will sum from J equal to what? From J equal to 1 to whatever, how many solutions there are. Length of US for, okay? And then we make a table from S equal to up to 8, okay? And and that's it, and we can monitor. We can have a dynamic here for S and J. Maybe that's okay. Okay, and we sum, we compute this, and we rationalize. After computing the sum, sorry. Each of them is not a rational number. Or let's do it even. Okay. Thank you. Only and we get precisely, you see, the values that this is still running, the one for spin 10. We get precisely the values in the lower diagonal. Okay? So if you see, if you take, let's do for example this last one, which is kind of fun. You take you compute the structure constant for spin, how much? 2, 6, 10, for spin 10. Okay? Let's see how many there are. Let's apply it. Let's compute this for all these guys. Okay. This is what we get. Okay. And it looks rather a list of that. And if we apply if we sum them all, we get this.
Can you go to the slide more?
Sorry. And if we rationalize, this gives exactly this number. Whereas each of them was not a rational number, it was a messy, messy number. Okay? And in the end, this is why we were using such high precision in solving bit equations, 850 digits, because we want to solve bit equations, plug them into the sum over partitions, do all these manipulations, get a number, sum all the numbers, and be able to recognize perfectly rational numbers that come from the expansion of rational numbers that are of rational functions that are the three-level scattering correlation function. Okay. So this is what is done here in this integrability section. It is just applied the total computing just what we just have done. Okay, and this gives exactly these numbers that appear in the upper diagonal. Okay, so this is if you want here, everything was derived. So it was important to have a handle on 3-point functions at strong coupling, at weak coupling, of course, and what we did is we derived the structure constant at weak coupling, and we just did a couple of fun checks by solving bit equations, summing them up, and so on. It should match with a conformal bootstrap, and it does, but we didn't need to check, it was derived. We just computed these scalar products, and it was a derivation, it is what it is. Whatever the result is, if we are going to plot this guy at any value of the coupling, when we turn off the coupling, it must reduce to this. And next time, what we will do is now go one step further into the unknown and try to ask, how about finite coupling? How about loops? How about we start correcting this guy? And this is really much trickier to do, for several reasons. We don't know the contact terms in general, so we don't know how to correct these wave functions. But even if we knew, it is no longer true that all we have to do is do weak contractions. We also need to do loops. We also need to decorate this guy by loops. And also, no one did these loops for us to tell us what the effect of these loops are. So, we are kind of in the dark in the sense that we want to be able to continue this study and to analyze these entire loops, but we are missing the knowledge of the wave functions and of the effect of doing Feynman loops, and we have to somehow circumvent this and being lazy, try to find a way of still getting the loop results without actually knowing the main ingredients. And we will do it by exploring our experience with integrability, and in particular with the analog quantity that we computed with Collier in the so-called SU2 sector, which is very much analog of the XXX spin chains that we saw in some of the lectures in the school. So tomorrow, the goal, I think it's a good time to stop, no? Am I too early? Am I stopping too early? Okay. So right now, this is the kind of expression that people have been playing with at 3 level, doing these combinatorial problems, playing with these spin chains, deriving expressions. At loop level, we will need to be a bit more inventive, and tomorrow will be both about loop level and about the more broad picture about how this fits within all other approaches, with a story at strong coupling, with a program for trying to really bootstrap this data, and so on and so forth. Okay, thank you.